Welcome to Advanced Database Management System. In this section, we discuss about importance of databases, data analysis and insights, scalability and performance, business continuity and disaster recovery, regulatory compliance. Let's enjoy. Databases are of paramount importance in today's digital age due to several key reasons. Data organization and storage. Databases provide a structured framework for organizing and storing vast amounts of data efficiently. By structuring data into tables, rows, and columns, databases enable easier retrieval, manipulation, and analysis of information. Data integrity and consistency. Databases enforce data integrity rules, such as constraints and validations, to ensure the accuracy and consistency of stored data. This helps maintain data quality and reliability, which is crucial for making informed decisions and conducting business operations. Data accessibility. Databases allow multiple users or applications to access and manipulate data concurrently, while ensuring data consistency and integrity. This enables collaboration among teams, supports real-time decision-making, and facilitates seamless integration with various applications and services. Data security. Databases implement robust security measures, including authentication, authorization, and encryption, to protect sensitive data from unauthorized access, manipulation, and disclosure. Ensuring data security is essential for safeguarding confidential information, complying with regulations, and maintaining trust with customers and stakeholders. Data analysis and insights. Databases serve as repositories for historical and transactional data, enabling organizations to perform in-depth analysis, generate reports, and extract valuable insights. By leveraging data analytics tools and techniques, businesses can uncover patterns, trends, and correlations that drive strategic decision-making and competitive advantage. Scalability and performance. Databases are designed to scale horizontally or vertically to accommodate growing volumes of data and increasing user demands. Whether it's adding more servers, optimizing query performance, or implementing caching mechanisms, databases provide scalability and performance features to ensure seamless operation and responsiveness. Business continuity and disaster recovery. Databases offer features for data backup, replication, and recovery to minimize the risk of data loss due to hardware failures, natural disasters, or human errors. Implementing robust backup and disaster recovery strategies ensures business continuity, reduces downtime, and protects against potential disruptions. Regulatory compliance. Databases play a crucial role in ensuring regulatory compliance with industry standards and government regulations, such as GDPR, HIPAA, PCI DSS, and SOX. By maintaining accurate records, auditing data access, and implementing appropriate security controls, databases help organizations meet compliance requirements and mitigate legal and financial risks. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about performance tuning, identify performance bottlenecks, set performance goals, optimize database design, indexing strategies. Let's enjoy. Performance tuning is the process of optimizing the performance of a database system to improve responsiveness, throughput, and efficiency. Here are some best practices for performance tuning in database management. 1. Identify performance bottlenecks. Conduct performance monitoring and analysis to identify bottlenecks and performance issues in the database system. Use performance monitoring tools database logs, and system metrics to pinpoint areas of concern. 2. Set performance goals. Define clear performance goals and objectives based on business requirements, user expectations, and service level agreements, SLAs. Establish benchmarks and performance metrics to measure progress and success in achieving performance targets. 3. Optimize database design. Design and optimize database schema, tables, indexes, and queries to minimize resource consumption and improve query performance. Normalize database schema to reduce data redundancy and improve data integrity. Use appropriate data types, constraints, and indexing strategies to optimize query execution. 4. Tune SQL queries. Identify and optimize poorly performing SQL queries that contribute to performance bottlenecks. Use query optimization techniques such as query rewriting, index optimization, query hints, and query plan analysis to improve query execution times and resource utilization. 5. Indexing strategies. Use indexes strategically to improve query performance by speeding up data retrieval operations. Identify frequently accessed columns and use indexes to support selective queries and search conditions. Consider the trade-offs between query performance and index maintenance overhead. 6. Database configuration. Configure database parameters, memory allocation, buffer pool size, and cache settings to optimize resource utilization and improve overall system performance. Adjust configuration settings based on workload characteristics, system resources, and performance requirements. 7. Hardware optimization. Optimize hardware resources such as CPU, memory, disk I/O, and network bandwidth to support database operations efficiently. Upgrade hardware components or scale out horizontally to accommodate increasing workloads and demand. 8. Query caching and result set optimization. Implement query caching mechanisms to cache frequently executed queries and result sets in memory, reducing query execution times and database load. Use stored procedures or materialized views to pre-compute and cache complex query results for faster access. 9. Partitioning and sharding. Consider partitioning and sharding strategies to distribute data across multiple physical or logical partitions, improving scalability and parallelism. Partition large tables based on access patterns, data ranges, or key values to distribute workload and optimize query performance. Monitor and tune regularly. Continuously monitor database performance metrics, system resources, and workload patterns to identify performance degradation and emerging bottlenecks. Implement proactive performance tuning strategies and conduct regular performance reviews and optimizations. Load testing and capacity planning. Perform load testing and capacity planning exercises to simulate production workloads, identify scalability limits, and ensure that the database system can handle peak demand and growth projections. Scale resources and infrastructure accordingly to accommodate increased workload and user concurrency. 12. Document and documentation. Document performance tuning efforts, optimizations, and best practices for future reference and knowledge sharing. Maintain up-to-date documentation of database configurations, tuning parameters, and performance monitoring procedures. By following these best practices for performance tuning, database administrators can optimize the performance of their database systems, improve user experience, and ensure that the database infrastructure meets the performance requirements and expectations of the organization. Regular monitoring, analysis, and optimization are essential for maintaining optimal performance and responsiveness in dynamic and evolving database environments. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about partitioning and sharding, range partitioning, hash partitioning, benefits of partitioning, benefits of sharding. Let's enjoy. Partitioning and sharding are techniques used in distributed database systems to horizontally scale and distribute data across multiple servers or nodes. While both approaches aim to improve database performance and scalability, they have different implementations and use cases. Partitioning. Definition. Partitioning involves dividing a large database table or index into smaller, more manageable segments called partitions. Each partition contains a subset of the data and can be stored on a separate storage device, server, or node. Types of partitioning. Range partitioning. Data is partitioned based on a range of values in a specific column. Example, partitioning by date ranges. Hash partitioning. Data is partitioned based on a hash function applied to a specific column's values. This ensures uniform distribution of data across partitions. List partitioning. Data is partitioned based on predefined lists of values for a specific column. Composite partitioning combines multiple partitioning methods. Example, range and hash partitioning to partition data based on different criteria. Benefits of partitioning. Improved performance. Partitioning allows queries and data retrieval operations to be distributed across multiple partitions, reducing contention and improving query performance. Scalability. Adding new partitions enables horizontal scaling of the database, accommodating larger data volumes and increasing throughput. Manageability. Partitioning facilitates easier management of large datasets by dividing them into smaller, more manageable units. Sharding. Definition. Sharding, also known as horizontal partitioning, involves distributing data across multiple independent database instances or shards. Each shard is responsible for storing a subset of the data, and data distribution is typically based on a sharding key. Key value sharding. In key value sharding, each shard is responsible for a specific range of keys or values. This ensures that data with similar keys are stored together on the same shard. Benefits of sharding. Scalability. Sharding enables linear scalability by distributing data and query load across multiple shards. As data volume and query throughput increase, additional shards can be added to handle the load. Fault isolation. Each shard operates independently, providing fault isolation and resilience. A failure in one shard does not affect the availability of other shards. Geographical distribution. Sharding allows data to be distributed geographically across multiple data centers or regions, improving data locality and reducing latency for users in different locations. Comparison. Partitioning, primarily used in single database instances, divides data within a single database, offers improved performance and manageability for large datasets. Sharding, used in distributed database systems, distributes data across multiple independent database instances or shards, enables linear scalability and fault isolation for distributed applications. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about NoSQL types of NoSQL databases, document stores, key value stores, column family stores. Let's enjoy. Definition of NoSQL. Key characteristics: flexible data models, scalability, high availability, distributed architecture. Document stores, key value stores, column family stores, graph databases. Explanation of document-oriented databases. Example: MongoDB, features and use cases. Explanation of key-value databases. Example: Redis, features and use cases. Explanation of column family databases. Example: Apache Cassandra, features and use cases. Explanation of graph databases. Example: Neo4j, features and use cases. Comparison of NoSQL and SQL databases, strengths and weaknesses of each approach. Big data applications, real-time analytics, content management systems, IoT data management. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about NoSQL databases, CockroachDB, key features of NoSQL databases, benefits of NoSQL databases, challenges of NoSQL databases, future trends in NoSQL databases. Let's enjoy. Definition of NoSQL. Characteristics of NoSQL databases. Combines the benefits of traditional SQL databases with scalability and performance as NoSQL, ACID compliance, distributed and horizontally scalable architecture. Overview of CockroachDB features. Distributed SQL database, strong consistency, horizontal scalability, multi-active availability. Native representation of relationships, efficient traversal of complex networks, schema flexibility, support for ACID transactions. Combines scalability of NoSQL with ACID compliance SQL, simplified data management with SQL interface, high performance for both read and write operations, horizontal scalability without sacrificing consistency. Data modeling complexity, managing distributed transactions, performance tuning for distributed queries, operational complexity in managing distributed clusters. Comparison of NoSQL with traditional SQL and NoSQL databases. Use cases where NoSQL databases offer advantages over other approaches. Advances in distributed SQL query optimization. Integration with cloud-native technologies, example, Kubernetes. Predictions for the future evolution of NoSQL databases. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about multi-model databases, multiple data models, unified data management, flexibility and agility, interoperability. Let's enjoy. Multi-model databases are database systems that support multiple data models within a single integrated platform. Unlike traditional databases that are typically designed for a specific data model, e.g., relational, document, graph, multi-model databases offer flexibility and versatility by allowing users to work with different types of data models interchangeably. Here are some key characteristics and considerations of multi-model databases. Support for multiple data models. Multi-model databases support a variety of data models, including relational, document, graph, key value, and time series. This enables users to store and query different types of data using the most appropriate data model for their use case. Unified data management. Multi-model databases provide a unified platform for managing diverse types of data, eliminating the need for separate databases or specialized tools for each data model. This simplifies data management and reduces complexity for developers and administrators. Flexibility and agility. Multi-model databases offer flexibility and agility in data modeling and schema design. Users can choose the most suitable data model for their data and easily adapt to changing requirements without the need for schema migrations or data transformations. Interoperability. Multi-model databases enable seamless interoperability between different data models, allowing users to perform complex queries and analytics that span multiple data types. This promotes data integration and facilitates cross-domain analysis and insights generation. Scalability and performance. Multi-model databases are designed to scale horizontally and vertically to handle growing data volumes and user loads. They provide efficient indexing, query optimization, and distributed processing capabilities to ensure high performance and scalability across diverse workloads. Data consistency and integrity. Multi-model databases ensure data consistency and integrity across different data models through transaction support, ACD compliance, and data validation mechanisms. They maintain data consistency constraints and enforce referential integrity to preserve data quality. Use cases. Multi-model databases are well suited for a wide range of use cases that involve diverse data types and complex data relationships. Examples include content management systems, e-commerce platforms, social networks, IoT data processing, real-time analytics, and fraud detection. Developer productivity. Multi-model databases enhance developer productivity by providing a unified API and query language for accessing and manipulating data across different data models. This reduces the learning curve and allows developers to focus on application logic rather than data management intricacies. Integration with existing systems. Multi-model databases integrate seamlessly with existing systems and data sources, enabling organizations to leverage their existing investments in infrastructure and applications. They support data migration, replication, and synchronization with legacy databases and external data sources. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about monitoring and alerting, monitoring tools, monitor key metrics, implement automated monitoring. Let's enjoy. Monitoring and alerting are essential components of database management, providing insights into system health, performance, and availability. Here are some best practices for monitoring and alerting in database management. 1. Define monitoring objectives. Define clear objectives and goals for monitoring, such as identifying performance bottlenecks, detecting anomalies, ensuring data availability, and meeting service level agreements, SLAs. 2. Select monitoring tools. Choose appropriate monitoring tools and solutions that meet the requirements of your database environment. Consider factors such as scalability, compatibility, features, and ease of use when selecting monitoring tools. 3. Monitor key metrics. Monitor key performance metrics such as CPU utilization, memory usage, disk I/O, network throughput, query latency, transaction throughput, and database connections. Track these metrics over time to identify trends and deviations from normal behavior. 4. Establish baselines. Establish baseline performance metrics for your database system under normal operating conditions. Use historical data and performance benchmarks to define baseline thresholds and detect deviations from expected performance levels. 5. Implement automated monitoring. Implement automated monitoring solutions that continuously collect and analyze performance data in real time. Use automated monitoring scripts, agents, or monitoring platforms to streamline data collection, analysis, and reporting processes. 6. Set up alerts. Configure alerts and notifications to proactively alert administrators and stakeholders about performance issues, anomalies, and potential problems. Set up alert thresholds based on baseline metrics, performance objectives, and criticality of the monitored parameters. 7. Define escalation policies. Define escalation policies and procedures for handling alerts and incidents. Establish clear roles, responsibilities, and escalation paths for responding to alerts, diagnosing problems, and resolving issues in a timely manner. 8. Monitor database logs. Monitor database logs, error logs, and audit logs for warning signs, error messages, and security events. Analyze log data to identify performance bottlenecks, security breaches, and operational issues that require attention. 9. Correlate metrics and events. Correlate performance metrics with system events, database activities, and workload patterns to gain deeper insights into performance trends and root causes of issues. Use correlation analysis to identify cause and effect relationships between different metrics and events. Conduct capacity planning. Use monitoring data and performance trends to conduct capacity planning and resource allocation. Forecast future capacity requirements based on growth projections, workload patterns, and performance trends to ensure scalability and optimal resource utilization. Regularly review and tune alerts. Regularly review alerting configurations, alert thresholds, and alerting rules to ensure that they remain relevant and effective. Fine-tune alerting parameters based on feedback, changes in workload, and evolving business requirements. 12. Document monitoring procedures. Document monitoring procedures, alerting configurations, and incident response workflows for reference and knowledge sharing. Maintain up-to-date documentation of monitoring tools, metrics, alerts, and escalation procedures. By following these best practices for monitoring and alerting, database administrators can proactively detect, diagnose, and resolve performance issues, ensure data availability, and maintain the health and reliability of their database systems. Continuous monitoring, analysis, and optimization are essential for effectively managing database environments and meeting the performance objectives of the organization. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about machine learning and AI in databases, natural language processing, NLP, data security and privacy, automated insights and data exploration. Let's enjoy. Machine learning, ML, and artificial intelligence, AI, are increasingly being integrated into databases to enhance their capabilities and provide more intelligent data management and analytics solutions. Here are some ways ML and AI are used in databases. Query optimization. ML algorithms can analyze query patterns and historical query execution data to optimize query performance. By learning from past query executions, ML models can suggest better query plans, indexing strategies, and database configurations to improve overall system performance. Recommendation systems. AI algorithms such as collaborative filtering and content-based filtering are used to build recommendation systems in databases. These systems analyze user behavior and preferences stored in a database to generate personalized recommendations for products, services, or content. Natural language processing (NLP) techniques enable databases to understand and process natural language queries and commands. By incorporating NLP capabilities, databases can support voice search, conversational interfaces, and text-based query processing, making data access more intuitive and user-friendly. Automated data management. AI-driven automation tools can assist in data management tasks such as data cleaning, data integration, and data categorization. ML algorithms can learn from historical data management activities to automate repetitive tasks and improve data quality and consistency. Data security and privacy. ML and AI techniques are used to enhance data security and privacy in databases. AI-powered systems can analyze access patterns and user behavior to detect potential security threats and anomalies. Additionally, NL models can help in data anonymization, encryption, and compliance with privacy regulations such as GDPR. Optimized resource allocation. ML algorithms can analyze resource usage patterns in databases and predict future resource requirements. By optimizing resource allocation, databases can ensure efficient utilization of computing resources such as CPU, memory, and storage, leading to cost savings and improved performance. Automated insights and data exploration. AI-driven data exploration tools can analyze large datasets stored in databases and automatically generate insights, trends, and patterns. These tools enable users to uncover hidden insights and make data-driven decisions without requiring extensive manual analysis. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about key value stores. Redis. Key features of key value stores. Benefits of key value stores. Best practices for working with key value stores. Future trends in key value stores. Let's enjoy. Definition of key value stores. Characteristics of key value databases. Basic data model. Pairs of keys and associated values. Simplicity and high performance. Scalability and fault tolerance. Overview of Redis data model in Redis. Key value pairs. Features. In-memory data storage. Support for various data types. Strings, lists, sets, etc. Pub-sub messaging. Built-in replication and clustering. Simple data model. Keys mapped to values. High performance for read and write operations. In-memory and disk-based storage options. Support for data types beyond strings, e.g. lists, sets, hashes. High performance and low latency. Scalability for handling large datasets. Simple data model and ease of use. Versatility in supporting various use cases. Comparison of key value and relational data models. When to choose a key value store over a relational database. Choosing appropriate data structures for keys and values, optimizing cache eviction policies, handling data persistence and backups, monitoring and performance tuning. Advances in in-memory computing technologies, integration with other data processing frameworks, e.g. Apache Spark, predictions for the future of key value databases. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about database management system, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about join operations, types of joins, inner join, left join, right join, full join, cross join. Let's enjoy. Join operations in SQL. Join operations allow you to retrieve data from multiple related tables based on a related column. Same types of joins. Inner join returns only rows that have matching values in both tables. Select e.name, d.department name from employees E. Inner join departments D on e-department ID equals DID. Left join or left outer join returns all rows from the left table and matched rows from the right table. Unmatched rows from the right will have null. Select e-name, D department name from employees E left join departments D on e-department ID equals DID. Right join or right outer join returns all rows from the right table and matched rows from the left table. Select e.name, D department name from employees E right join departments D on e-department ID equals D.ID. Full join or full outer join returns all rows when there is a match in one of the tables. SQL select e.name, D department name from employees E full join departments D on e-department ID equals D.ID. Cross join returns the Cartesian product of both tables, every combination. Select E name, P project name from employees E, cross join projects P. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about database management system, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about isolation levels, read uncommitted, read committed, repeatable read, serializable. Let's enjoy. Isolation levels define the degree to which the transactions in a database system are isolated from each other. Different isolation levels provide different trade-offs between data consistency and concurrency. The commonly used isolation levels are defined by the SQL standard, and they include read uncommitted. In the read uncommitted isolation level, transactions are not isolated from each other. This means that a transaction can see uncommitted changes made by other transactions. Read uncommitted provides the highest degree of concurrency, but sacrifices data consistency, since transactions can read dirty data that has not been committed yet. Read committed. In the read committed isolation level, transactions can only see committed data. This means that a transaction cannot read data that has been modified but not yet committed by other transactions. Read committed isolation level prevents dirty reads but allows non-repeatable reads and phantom reads. Repeatable read. In the repeatable read isolation level, a transaction sees a consistent snapshot of the database at the time the transaction starts. This means that any data read by the transaction remains unchanged during the transaction's lifetime, even if other transactions modify or delete the data. Repeatable read prevents dirty reads and non-repeatable reads, but allows phantom reads. Serializable. In the serializable isolation level, transactions are completely isolated from each other. This means that transactions execute as if they were the only transactions running on the database. Serializable provides the highest level of data consistency, but can lead to decreased concurrency and increased contention due to locking. Snapshot isolation. Snapshot isolation is a variation of the repeatable read isolation level that provides a consistent snapshot of the database at the time the transaction starts. However, unlike repeatable read, snapshot isolation allows other transactions to modify the data concurrently. Each transaction sees a consistent snapshot of the database, but it may see different versions of the data modified by other transactions. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about indexing and query optimization, types of indexes, benefits of indexing, query optimization techniques for query optimization. Let's enjoy. Indexing and query optimization are essential techniques used to improve the performance of database systems by speeding up data retrieval and query processing. Here's an overview of indexing and query optimization. Indexing. What is an index? An index is a data structure associated with a database table that allows for efficient retrieval of data based on certain columns or expressions. Indexes provide a quick lookup mechanism, similar to the index of a book, allowing the database to locate specific rows quickly without scanning the entire table. Types of indexes. B-tree index, the most common type of index used in database systems. It stores keys in sorted order, allowing for efficient range queries and equality searches. Hash index uses a hash function to map keys to index entries, providing constant time lookup for equality searches but not supporting range queries. Bitmap index, suitable for columns with low cardinality, where each bit in the index represents the presence or absence of a value. Full text index, designed for efficient text searches, supporting operations such as word searches and phrase searches. Spatial index, optimized for spatial data types, enabling efficient retrieval of spatial objects based on their geometric properties. Creating indexes. Indexes can be created using SQL commands such as create index. You specify the table and column S to be indexed, and the database system creates the index accordingly. Benefits of indexing. Improved query performance. Indexes speed up data retrieval operations, especially for columns frequently used in search conditions or join predicates. Enhanced data integrity. Unique indexes enforce uniqueness constraints, preventing duplicate values in indexed columns. Support for constraints. Indexes can be used to enforce primary key, unique key, and foreign key constraints. What is query optimization? Query optimization is the process of improving the performance of database queries by selecting efficient execution plans. The goal is to minimize query execution time, reduce resource consumption, and improve overall system efficiency. Query execution plans. A query execution plan is a sequence of operations performed by the database system to retrieve and process data requested by a query. The optimizer generates multiple execution plans and selects the one with the lowest cost based on factors such as access methods, join algorithms, and index usage. Techniques for query optimization. Cost-based optimization uses statistical information and cost models to estimate the cost of executing different query plans and selects the plan with the lowest estimated cost. Query rewriting transforms the original query into an equivalent form that can be executed more efficiently. Techniques include predicate pushdown, join reordering, and subquery optimization. Index usage identifies and selects appropriate indexes to access data efficiently. The optimizer considers index selectivity, cardinality, and access path options. For example, index scans, index seeks, join optimization, determines the most efficient join order and join algorithms. For example, nested loop join, hash join, merge join, based on the size of the tables, join conditions, and available indexes. Parallel execution executes queries in parallel across multiple CPU cores or nodes to exploit parallelism and reduce query execution time. Monitoring and tuning. Query performance should be regularly monitored using tools such as database performance monitors and profiler tools. Performance bottlenecks can be identified and query optimization techniques can be applied to address them. This includes creating or modifying indexes, rewriting queries, or adjusting database configuration parameters. Effective indexing and query optimization play a crucial role in improving database performance, reducing query response times, and enhancing overall system scalability and efficiency. By utilizing appropriate indexing strategies and optimizing query execution plans, database administrators can ensure optimal performance and responsiveness of their database systems. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about in-memory databases, implementation considerations, challenges and limitations, future trends. Let's enjoy. Overview of the architecture, data storage in main memory, mechanisms for durability and persistence, snapshots, transaction logging, replication, memory requirements, data persistence strategies, scalability options, integration with existing systems, memory requirements, data persistence strategies, scalability options, integration with existing systems, memory constraints, cost considerations, data persistence complexities, integration challenges with existing infrastructure, continued adoption and growth of in-memory databases, advances in memory technology, for example, non-volatile memory, integration with emerging technologies, for example, AI, edge computing. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about edge computing databases, proximity to data sources, low latency processing, offline operation, distributed architecture, resource efficiency. Let's enjoy. Edge computing databases are database systems specifically designed to operate at the edge of the network, closer to the data sources and end users. These databases are optimized for low latency, high throughput data processing, and storage in edge computing environments. Here are some key characteristics and considerations of edge computing databases. Proximity to data sources. Edge computing databases are deployed closer to the data sources, such as IoT devices, sensors, and edge servers. This proximity reduces latency and network bandwidth usage by processing and storing data locally at the edge. Low latency processing. Edge computing databases prioritize low latency data processing to support real-time applications and services at the edge. They minimize data round-trip times and response times by executing data processing tasks locally without relying on centralized cloud servers. Offline operation. Edge computing databases are designed to operate offline or with intermittent connectivity, as edge environments may experience network disruptions or limited connectivity. They provide mechanisms for local data storage, caching, and synchronization to ensure data availability and continuity of service. Distributed architecture. Edge computing databases employ distributed architectures that span multiple edge nodes or devices. They support data replication, synchronization, and consistency mechanisms to maintain data integrity and availability across distributed edge environments. Resource efficiency. Edge computing databases are optimized for resource-constrained edge devices with limited compute, memory, and storage capabilities. They minimize resource usage by employing lightweight data storage formats, efficient indexing structures, and data compression techniques. Edge analytics. Edge computing databases support real-time analytics and data processing at the edge, enabling edge devices to analyze and act on data locally without the need to transmit data to centralized servers. This enables faster decision-making and reduces reliance on cloud-based analytics. Security and privacy. Edge computing databases implement robust security features to protect data at the edge, including encryption, access controls, authentication, and data anonymization. They ensure data privacy and compliance with regulatory requirements, such as GDPR and HIPAA, in edge computing environments. Integration with cloud services. Edge computing databases seamlessly integrate with cloud services and centralized data platforms, enabling hybrid cloud edge deployments. They support data synchronization, replication, and streaming between edge devices and cloud-based databases for centralized data analysis and storage. Edge cloud orchestration. Edge computing databases work in conjunction with edge cloud orchestration platforms, such as Kubernetes or Docker Swarm, to manage and orchestrate edge computing resources. They support containerized deployments and microservices architectures for scalable and flexible edge deployments. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about graph databases, Neo4j benefits of graph databases, key features of graph databases, best practices for working with graph databases, future trends in graph databases. Let's enjoy. Definition of graph databases. Characteristics of graph databases. Data represented as nodes, edges, and properties. Optimized for traversing relationships. Use cases. Social networks. Recommendation engines. Fraud detection. Introduction to Neo4j. Data model in Neo4j. Nodes, relationships, properties, features. Native graph storage and processing, Cipher query language, ACID compliance, high availability clustering, native representation of relationships, efficient traversal of complex networks, schema flexibility, support for ACID transactions, natural representation of connected data, high performance for relationship-heavy queries, flexible schema evolution, powerful graph algorithms and analytics, comparison of graph and relational data models, use cases where graph databases excel over relational databases, effective data modeling strategies for graph structures, optimizing queries and indexes, cluster configuration and optimization, monitoring and maintenance practices, advances in graph algorithms and analytics, integration with machine learning and AI technologies, predictions for the future evolution of graph databases. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson.